Technology Policies Distinguished Seminar Series, where it's an incredible privilege to welcome the founding director for the Center for Information Technology Policy. Ed has been Professor Emeritus, the Warburg Econ Professor Emeritus in Computer Science and Public Affairs. He was a faculty at Princeton for more than 28 years. So I don't think it needs a big introduction for me. I'm sure all of you want to hear more from him. But I'll just mention a couple of examples of the impact that his work has had at Princeton and the legacy that he's left at the center. So it started the Freedom to Tinker blog, which is one of the most widely read blog posts back in the early 2000s. It started graduate certificate programs at the intersection of technology and society, which have turned out to be incredibly popular. Ed is now the chief scientist and the co-founder of Offchain Labs, and you'll hear from Ed about that more today. Ed, on behalf of the Center for Information Technology Policy, thank you for all of your efforts, and it's great to have you back, and I'm looking forward to both the talk and the reception following that.
Thank you. Thanks, Pratik, and it's great to be back at Princeton and great to see so many familiar faces. I've been looking forward to coming back and visiting and giving a talk about this for some time, so really happy to be here and doing it now. So I want to tell the story about how a piece of research that we did here, starting in 2014, turned first into more mature academic work, and then turned into a product and company that has now been growing. And I'll talk partly about the story of how this started and kind of the journey that we've gone through. But I'm a computer scientist, so I'm also going to spend a big chunk of time talking about the technology we've built and how it works. OK, so the story starts with in 2014, when CITP ran one of the first academic conferences on blockchain and cryptocurrency tech. This was in March of 2014. We brought a bunch of the leading developers of then Bitcoin, which was all there really was at the time, back here, and we started to talk about what was going on, what were the interesting problems in the space, where was it likely to go, and so on. During that conversation, during that conference, during the conversations there, I think over the cocktail hour, if I remember correctly, I got into a conversation with one of the visiting developers about the problem of scaling and how we could scale smart contract technology. I'll talk a little bit in a minute about what that is, but this was one of the coming things in the field. It was something that had been thought up, had not yet been put into the field. And it was obvious, at least to me at the time, that there was going to be a big problem with scaling this up to a practical level of use. And so that led to some thinking about how you might be able to provide the same functionality at lower cost, higher scale. And that ultimately led to the birth of the idea that through many evolutions over time turned into what we are now offering. So it all started at a CITP conference. OK, so let me talk a little bit about the technical background of what it is that we're doing. So there's this term in the blockchain space called smart contracts. Smart, as you know, means nothing when applied to some technical thing. And these things are not contracts. So as so often in the blockchain space, the terminology is terrible, but the reality of it is actually interesting. OK, so basically, the idea behind this is that you can have a blockchain that, in addition to supporting ownership and movement of assets like Bitcoin did, also allows you to run on the chain untrusted computer programs. Those are the so-called contracts. So there's a special transaction type that that a smart contract-enabled chain supports that you can use to install a program on the chain. And then once you've installed a program, one of these contracts, it then becomes a first-class actor in the system. And it can do pretty much anything that a person could do. So they can call other contracts. The user can send signed transactions to the contracts to make things happen. So what this means is that instead of just being a way to move money around, this is a platform for building applications. And it's a platform that has different and interesting characteristics compared to other platforms that you can use. So you can think of it basically of one of these chains as being like a virtual shared computer that is shared among all of the users of the particular system all around the world. Now, all of the code that is installed on this thing is visible. That means everyone can see the code. They can see it in whatever format it's in. You can disassemble it, analyze it, and so on. And the code is guaranteed to execute. Each contract is guaranteed to execute according to its code because the blockchain consensus system ensures that that's the case. So it's a virtual shared computer where everyone can see what's happening inside the computer, and you know that it's going to execute according to its code. Okay, so Ethereum is the first example of this that came into existence and the leading example. Among smart contract-based blockchains, Ethereum has maybe 55% of the usage share. Okay, so why do this? There's a common sort of argument that people sometimes put out there that why would you do this? It's just like a database in the cloud. Anything you can do with this, you can do with the database in the cloud. I want to take a minute and stop, because I know my audience, and talk about why I think that argument is not correct. For one thing, we need to think clearly about what the cloud is. There is no such thing as the cloud. It's just someone else's computer, as the slogan goes. Right? If you're using a cloud-based service, that service is running on someone's computer. And that someone gets to control what the code of the service is, and what you get to know about what that code is, and when that code can change. So basically, that party has all of the power in the interaction, fundamentally, because they control what's going to happen, how, and when. You don't even get to know what's going to happen. So if you just assume away that problem, then yes, a smart contract is just a database in the cloud. But that problem is a really big problem in practice. This is why people say big tech companies have too much power. Because they have that control, because the stuff runs on their computer and not yours. So having a neutral space that is not your computer, not their computer, but you get to see what's happening on it, gives you a different model and a different way that you can express the trust relationships in what's happening. So it's a shared computer where mutually untrusting programs can coexist safely without needing to trust that someone operating that computer is going to behave honestly. And the operation of it is transparent and predictable. Again, unlike someone else's computer. Now, transparency and predictability don't solve all problems, just like transparency in government doesn't solve all governance problems, but it helps. And you're better off living in a world where transparency is one of the things you have available to you. You get to know what the code is. You get to know under what conditions it can change. And that is an important tool if you want to build systems and relationships and architectures that are more even-handed in their power relationships. Okay, so here's another way of looking at what this is. In practice, this often serves as a general-purpose platform for building distributed protocols. Why is that? Well, if you know how computer scientists who study distributed computing protocols think about them, the standard way to go about designing a protocol is you design an idealized version of your protocol that depends on a trusted third party. You then design some complex distributed protocol, and you prove that it is in some sense equivalent to the idealized trusted third party protocol, right? So that in some sense, anything that can happen in your distributed protocol is a thing that could have happened with the trusted third party, and then you can operate safely without a trusted third party. So that's the way a lot of distributed computing research works when you want to design a protocol. That's really hard to do, to design the protocol, to do the proof, to get it deployed and developed, very difficult to do. Instead, if you have a smart contract-based blockchain, what you can do is define your protocol in terms of an idealized trusted third party, define that trusted third party's behavior in code, install that on the blockchain as a contract, and now you have an actual trusted third party, an entity that will behave according to certain rules reliably, and you don't have to trust any particular party to behave in that way. So this makes it much easier to design and evolve distributed protocols. And in practice, a lot of the products that launch on these systems call themselves protocols, and that's for a reason. They really are, in some deep sense, protocols rather than simply pieces of code. So this is actually a really powerful mechanism that a lot of people are using. It's easier to compose multiple protocols when they're built in this way, and there's this notion of protocol Legos, where one protocol can depend on another protocol in a way that's much easier to arrange than if they're built in a more traditional and laborious way. So this is actually a fairly powerful mechanism for designing new types of functionalities that operate in new types of trust relationships. But here's the big problem. Capacity on these systems is very limited. Ethereum is a globally shared virtual computer. That's awesome. The not so awesome part is it has about the computational throughput of a 5-year-old laptop to be shared among all people in the world. That is really limiting. Now resources, because it's a public and open system, resources are rationed on the system by an economic mechanism. You pay as you go, and the price adjusts automatically to balance demand with capacity. And so that means limited capacity leads to high price. And so these systems are both very limited in capacity and very expensive unless you do something. So this brings you back to the place in the story where we were talking about how to make smart contracts have higher capacity and lower cost. This is the problem which we set out to solve starting back in 2014. And this is the problem that has really motivated a lot of the development of the tech and of our company. Okay, so let me talk about layer 2. The idea of layer 2 is to take a system like Ethereum, but move most of the work that is done by the system, move it to a protocol that's executed by untrusted users with just a kind of small referee component to anchor the security in a small component that's on Ethereum. That is, instead of having Ethereum itself execute or emulate all of the programs that are installed on your chain, instead lift that up to a higher level protocol, so-called layer 2 protocol, and have just a small centralized trusted component that runs on Ethereum and has a small footprint. But if you do this right, you can get the security of Ethereum at much lower cost. And I'll describe in perhaps excruciating detail later how we do that. But this layer 2 idea is very popular these days, and the original Arbitrum design from 2014 was probably the first layer 2 design. We actually have evidence of that. Here is, this is a video on YouTube from January of 2015. This is a student course project in a course that Arvind taught on blockchain technology in the fall 2014 semester here. And you can see that it says Arbitrum up at the left. There is the strangely anarchy-like logo, which is no longer used. And you can see the students explaining this. So the students built, based on the original idea that we cooked up at this conference in March, these students in the fall working with me built a very, very early sort of proto-Arbitrum system. And you can watch their course presentation on YouTube if you like. So fast forward by a couple of years, and we ended up publishing. So after that, the system sat idle for a few years. Those of us who were working on it went off. We did other things. We came back and picked it up again in early 2017. And we ended up building an academic prototype of the system, which was somewhat more complete, but also an academic prototype, meaning that it worked well enough that we could write a paper about it, but it was nothing like a complete or reliable product. We published this paper in the Usenix Security Symposium in the summer of 2018. And the lead authors on it were Harry Kolodner and Stephen Goldfeder, who were then PhD students. So this described a version of Arbitrum. At that time, we realized that we had this technology that solved what we what we thought was a real commercial problem for users of these systems. Our thesis was that the cost of using resources on Ethereum was going to go up a lot, and that we had a way to reduce it by perhaps a factor of 10, and that other people didn't seem to have a solution to this problem. So we thought, well, maybe we can commercialize this. And so the company was founded. Here are your 3 co-founders sitting at Tiger Labs up on Nassau Street in early 2019. This is when we really became a company, and you see the full staff of the company at that time right here. This is a photo that I think we used for our first fundraising round. So we started in 2019. I'll talk a little bit later about the progress that we made since then, but suffice it to say that as of today, the team looks more like this. We have currently 70 people in 19 countries, and it's grown to a tremendous extent from where it was, as well as going through several stages of evolution of the technology. Okay, so what is it that we provide? So the basic value proposition that we set out to provide, and the thing that we started working on when we decided, okay, we have a really nice academic prototype published in a great place. How do we turn it into an actual product? We said, okay, here's the value proposition. We want to give you everything you like about Ethereum, the same virtual machine, the same transaction formats. So you literally send the same bits you would send to Ethereum if you want to do a thing. The security derived from Ethereum, you can call to and from Ethereum or transfer assets, and use the same native currency as Ethereum. So just like Ethereum, if you like Ethereum, which is a leading smart contract-based system, you'll like this. But better in a bunch of ways. 20x cheaper, 5x more capacity, and a 20x faster response time. So that when you push a button to do a transaction, it's about half a second response time instead of 15 seconds. Okay, so how do we do that? All right, now we get to the computer science part of the talk. Fundamentally, in an abstract level, what the system does is just this over and over really fast. So a transaction comes in, that's just some string of bytes signed by a user that describes a thing that's supposed to happen in some smart contract. The transaction feeds into the state transition function. This is just a deterministic function defined by some code. The state transition function takes that transaction and the current state, and it produces as output a new block in the blockchain describing the result of that transaction, as well as an update to the state. The system logically just does that over and over really fast. But in order to actually provide that and provide it in a way that has the security you need, operates at the scale you need, we have to do a bunch more complicated stuff. So let me give you Arbitrum in a nutshell. And rather than sort of giving you the complete architecture diagram or too much of it, I want to talk about 4 main ideas which kind of fit together to build the technology. Optimistic fraud proofs, sequencing followed by deterministic execution, Geth at the core, and yes, I'll explain what that means, and separating execution from proving. Let me start with optimistic fraud proofs. This is the original idea that, starting in about March 2014, was on my office whiteboard in Sherrod Hall for most of that year. And it goes basically like this. So suppose you have some start state, some state of the system, which is already established as correct. How are you going to make progress? How are you going to figure out what the next state is or what results from executing a bunch of transactions? So you start by some person who I'll call Alice makes a claim that starting in this known start state, that the system can generate n new blocks and the result will be some end state. Now, Alice is not announcing the complete start state and end state, just some hash of the state for compactness, but it amounts to the same thing. Alice is making a claim about what the progress of the system will be. Now the system is optimistic. What that means is we start a timer. And if anyone disagrees with Alice, they're supposed to speak up. If some time interval passes and no one disagrees with Alice, then the system will accept this claim as correct. If someone disagrees, then we're going to have a dispute resolution protocol that will operate. Now the parties in this protocol are all, in order to make a claim, you have to put down a stake. That is, you have to deposit some actual money, and which you will lose if your claim is proven to be wrong. So Alice has incentive not to make a false claim, And if Alice makes a true claim, then everyone else has incentive not to challenge it. So if everyone obeys their incentives, someone will make a claim, no one will dispute it, and you move forward, and you don't even need to check anything. Right? And all this relies on is the assumption that there is some honest party, or at least some greedy party who's paying attention, so that you can make progress and have it be correct. All right, now, so I've color-coded, yes, Pratik.
Isn't there an inherent assumption here that there is some reachability property that honest nodes have to the system, because you could do denial of service attacks?
Absolutely right. So this is one of the really interesting technical details about how the protocol works, is how we deal with the possibility of denial of service against the parties. So we have a formal threat model which says essentially that when someone wants to do a transaction, they can do it within 5 minutes unless the system is in censorship mode. And there's an adversary who can turn censorship mode on and off, but it can only be on for a total of 7 days. And we prove our protocol correct under that threat model. All right, so the delay is long enough, and we think in a really systematic and precise computer science-y way about this. All right, so I've color-coded this stuff here. Right, the start state is black because that is known to be correct. The end blocks is also black because, for technical reasons I don't want to go into, we know that the system can generate end blocks. The thing at the end is orange. That means that it's just a claim that Alice is making, and it hasn't been substantiated as correct yet. Okay, so Alice makes this claim. Let's suppose that Bob responds and says, Bob says, no, I disagree. Okay, so Bob says, well, he can't dispute the start state because that's already established. The end state, Bob makes a claim about the hash of the end state that differs from Alice's claim. Okay. Now, we tell Bob, okay, if you disagree, tell us what the midpoint state is. Tell us what the state hash is after n over 2 blocks. Don't just disagree with Alice. All right, so Bob does this. Now, we go to Alice and we say, okay, Alice, do you agree or disagree with Bob's claim about the midpoint state? And Alice has to say one or the other. She agrees or she disagrees. So Alice can respond. Alice can either say, I disagree with Bob's mid state. Then she has to say what mid state she claims that's different. And notice that if we do this, now Alice and Bob disagree about just the first half. We know that they agree on this start state because it's fixed. They disagree about the mid state. So now if Alice says this, that she disagrees with Bob's mid state, now we have a disagreement of n over 2 blocks about the first half of this span of blocks. The other thing Alice can say is, no, she agrees with Bob's midpoint. And in that case, well, now they agree on the mid state. We can turn that black. And now they have a dispute about the second half. So either way, whatever Alice says, we've taken a disagreement about n blocks, and we've reduced it to a disagreement about n over 2 blocks. And notice that the referee who's refereeing this doesn't even need to think about the merits. Right? I haven't said anything about the merits of who's right. This is just a very simple, okay, Alice, your move. Okay, Bob, yes or no. Back and forth. All right, now we're computer scientists, or many of us are, and we know what happens next. We do the same thing again recursively, right? So Alice, let's say she says she agrees with the mid state, disagrees with the end. Now we make her bisect that. Say what is the state after 3n over 4 blocks from the beginning. Now the ball's in Bob's court. Does he agree or disagree with that, and so on. After log n rounds of this, we have a disagreement about a single block. And again, nobody's talked about the merits. It's just this back and forth mechanism. Okay, so how does the challenge protocol really work in practice? Well, it's a little more complicated than what I said, but that core idea. Alice claims the result of n blocks. If Bob disagrees, you bisect the disagreement down until it's a disagreement about just one block. Now you open up that block and look inside. The block was created by the execution of a particular piece of code. That code happens one instruction at a time. And so now you have a disagreement about the execution of some number of instructions of machine code or something like it. So within that block computation, you can further bisect that disagreement about a sequence of instructions down to a disagreement about one instruction, like one add instruction. You're adding 3 and 4, and what's the result supposed to be? Once you've bisected down to one instruction, now Alice has to submit a proof of that one instruction. And so the beauty of this is if you're the referee who has to referee this dispute, it's purely a mechanical checking process of did people move when they were supposed to? Was their move properly formatted? A little bit of bookkeeping about what are we disagreeing about now? And then you have to check at only one instruction by just symbolically executing that instruction. Andrew?
And how much wall clock time should we imagine that whole process takes?
The whole process takes 7 days, and the reason is this 7-day threat model. It takes 7 days plus a little bit in practice. Yeah, it's actually, again, a very interesting question, and one on where we have a forthcoming research paper. How small can you make that, and how much can you make the cost for honest parties, especially if there are multiple dishonest parties participating? Super interesting research problem.
In other words,
there.
we're going to address the question of, it's worth it to Bob to delay a certain real-world transaction
Yep.
for 7 days.
Yeah.
Pay the cost of a failed dispute resolution.
Right, so someone can sacrifice. So there's an important distinction here. He's not delaying the execution of the transaction. He's delaying the recognition, the certification of that result on Ethereum. I'll talk about this in a minute. Let me put that off, yeah. All right, let me talk about the next piece of the design. So that's the dispute resolution protocol. And that was kind of the core idea that started it all, that you could resolve a dispute about the execution of a lot of complex code, perhaps something like 2 to the 45 instructions, and you could resolve it relatively efficiently. Okay. The next part of this, the next piece of the system is how we separate sequencing from execution. All right. So I'm going to tell you again, I'm going to build a kind of architecture diagram of what happens to transactions as they run through the system. So there's a component called the sequencer, which is importantly trusted only to say in what order it received transactions. It's not trusted for any other purpose. So transactions get sent to the sequencer. The sequencer produces an output sequence. It says, these are the ones I saw, and this is the order in which I saw them. Okay. Then, and this part will look familiar, these transactions can be run one at a time through the state transition function, updating a state and producing a sequence of blocks. Now, this sequencer component is a single component that lives out there on the network, and it produces the sequence. And I'll talk in a minute about how people learn what the sequencer produces. But the important thing about the right-hand side, this execution layer, is that every honest party can execute this independently and separately for themselves. If you know the sequence of transactions that have happened, and you know what the starting state was, you can privately execute all of these transactions yourself and know what the state of the chain is. So in order to know what happened on the chain for yourself, you can just do this yourself. You don't need to rely on anybody else. Now, you might choose to trust someone else to do that for you. That's fine. You're welcome to do that. You can rely on multiple parties and check them against each other. But in principle, anyone can do this execution part of the protocol for themselves and know what the correct result is. And this is the case because the initial state is known and this state transition function is deterministic. So there is a single correct answer as to what these blocks will be. Okay, so how do people know what the sequencer has done? And the answer is 2 things. First, the sequencer publishes immediately a feed of all of the transactions it has sequenced. It's a signed feed. It goes out within a fraction of a second and gets sort of blasted out into the world, signed by the sequencer. And so this is the sequencer's promise that it will very quickly, typically within a minute, record these transactions officially on the Ethereum chain. Now, the reason we do this is that we want to be able to give people a really fast response time, a fraction of a second, but Ethereum only makes a block every 12 seconds. So we can't even wait for Ethereum to make 1 block to record this information. So we blast out this feed, and because of the technical design of the protocol, the sequencer always has the power to keep its promises about this. And so the only way that this could fail, absent a horrible technical failure at the sequencer, is that the sequencer is dishonest. So if you choose to trust the sequencer to tell you the truth about what it will do a minute from now, a promise that is checkable, then you can move forward with confidence that you know the result of your transaction. If you want to wait, you can wait, and about every 45 seconds to a minute, the sequencer will take a big batch of these transactions, batch them together, compress them using a general purpose compression algorithm, and then post them on the Ethereum chain. And this Ethereum chain is public, and so anything that's posted here is known to everyone. So this serves as a tamper-proof ledger of all of the batches that have been posted here. So if you want to wait that long, then your batch will be posted on Ethereum, and then you know. And at that point, the result of your transaction is irrevocably decided, because this is the final and canonical record of what the transaction sequence is, and this part is deterministic, and so everyone knows what the result is. Now, Scott.
Where does the sequencer live?
I was just going to ask that.
The sequencer, so currently the sequencer lives in a corporate data center somewhere. It's operated by our team. We've promised to our community, and we have a design for decentralizing the sequencer, so it's operated by a consensus committee. But remember, the sequencer's only role is to vouch for the order in which it received transactions. There's another mechanism that prevents the sequencer from censoring transactions, from keeping them from getting on chain. I've omitted that to simplify the description. So its only power is to manipulate transaction ordering. It's not trusted for any other purpose. Yes?
How is the composition of that committee decided? Is that decentralized, or is it Ethereum style?
Currently, it's not. Currently, that isn't implemented yet, so there's not an answer to that yet. We have plans, but we haven't announced yet how that will be chosen. Essentially, because it is a sort of K of N trust kind of relationship, you want a set of parties that are widely trusted by the community of users.
You started off this talk by talking about the cloud being somebody else's computer. So to some degree, the sequencer does have that.
Yes.
Obviously, it lives in a
But-
data center operated by a team. So what are the implications of
Yeah.
misordering transactions?
Yeah, so misordering transactions, essentially by manipulating the transaction order, it's possible to extract value in financial trading by doing things like front-running users. Yeah. So that is the power of the sequencer. The sequencer does not have the power to make a transaction the transactions are all digitally signed by the users, and their execution is all certified by a mechanism I'll talk about in a minute. And so it's only transaction ordering that the sequencer is trusted to do, and nothing else. It doesn't have the power to exclude transactions. It only can affect ordering. And it's true that there's some ability to manipulate, which of course, we operating the system double pinky swear that we won't do. But having a committee do it is better. And there's some more advanced research that actually that at least in principle can allow you to detect cheating.
How about data availability? If someone wants to get back the original data?
Yeah, they get it from Ethereum.
With your compressed version,
It's compressed, right, but it's compressed using general purpose, using Brotli, which is a general purpose open source compression algorithm, so anybody can run that. Yeah. No, it's not a hash. It really is compressed. Yeah, so that, and of course, we publish open source code as well as a specification for the decompression. Yeah. So, and by the way, this is the most expensive part of the system, is posting this on Ethereum. And this operation right here is the largest single user of Ethereum in the world. Okay. The remaining step that I haven't shown you is the step of certifying these results. Remember, any honest party knows what the correct result is immediately, or as soon as this batch is posted, which is about once per minute. Certification of the result back to Ethereum, which basically creates a checkpoint which anyone can trust, happens via that assert and challenge protocol later. So if you want to know what the result of your transaction is and be able to demonstrate it to any other honest party, that happens after about a minute. If you need to certify the result on Ethereum, which is really only the case if what you're doing is moving an asset from the Arbitrum chain onto Ethereum, That may take up to 7 days, but there are services that will do it for you fast because they know with certainty that your withdrawal will happen. So you can, there's a protocol called cross-chain atomic swap you can do between the chains that give you fast ability to give someone some asset on the Arbitrum chain and get back the same asset on the Ethereum chain atomically. And that's what people actually do in practice. Okay, so that was actually my next topic. How do you get finality? There's soft finality. After maybe half a second, you subscribe to the sequencer feed, compute the state transition function, et cetera. That's correct if the sequencer's feed was correct, was honest. There's this finality on Ethereum. Most of that is waiting for Ethereum itself to get finality. That takes about 5 minutes. And that gives you an absolute guarantee of what the result of the transaction is. And then there's the certification, which takes about 7 days. Yes?
Question about the previous slide. Simple question. The transactions are sequential, but what if there's feedback going on between any one transaction depending upon what happens to another transaction?
Well, right. The transactions execute logically on the chain one at a time. And so each one executes in the state that holds when that transaction gets to the head of the queue, logically. There can't be a circularity. You can't express the thought of a circularity. Your transaction operates on whatever the current state is.
You just did express the thought.
I'm sorry, you can't. I'm sorry, right? You can express the thought clearly, and it's an excellent question. But what I should have said is that each transaction, when it executes on the current state. It's not allowed to know what transactions are after it in the queue. Because this function is deterministic, it depends only, the result of your transaction can depend only on the transactions that happened before it and the contents of your transaction. It cannot depend on a transaction that comes afterward because it has no way of seeing or looking at or asking for the contents of future transactions. The execution rules just don't allow that kind of dependence. You can submit transactions whose results will depend on the order of them, but then you get whatever result you get depending on when they arrive at the sequencer.
How is output state, the state transition function, blocks propagated around the network?
There's two answers to that. The first one is that it doesn't need to be propagated because everyone can do this for themselves separately and independently. If you don't want to do this, if you don't want to execute this yourself, you can then just rely on someone else to do it. There are commercial node services that will do this, and you just send a remote procedure call, a query to them. So there's no need to propagate the results because the results because everyone can figure out the results for themselves independently.
Maybe there's not like a front running issue with the transactions going into the sequencer, but if you can get the state out of the state transition function first and act on that and put in your...
Yeah, so the question is, what you really want to do if you're that person is get early access to the sequencer feed, right? Because this is the record of the transactions that have happened. The sequencer keeps secret which transactions have been submitted but not yet sequenced. That's actually important to prevent third parties from front running. That's called the secret mempool. That's one of the important properties. People do want to get fast access to the sequencer feed, and they do all kinds of abusive stuff to our sequencers, to our sequencer servers to try to get it. There's a whole arms race there. But fair access to that sequencer feed is actually quite important. Okay, move forward to the next one. Okay, the next piece, Geth at the core, and yes, I'll explain what Geth is. See, Geth. No, so Geth is Go Ethereum. That is the most common, most popular, most widely used node software for Ethereum. So Ethereum executes in the Ethereum virtual machine, or EVM, and the software that most people use to actually be a node in the Ethereum network is Geth. Geth has a bunch of things in it. It has an EVM emulator. It's got a bunch of bookkeeping, a database. It's a network server and a bunch of other stuff. We take the core of Geth, the part that emulates the Ethereum virtual machine, and we compile it into our code. And the beauty of doing this and sort of getting that separation is that we use even though Geth was not designed to have its core be a library that operates this way, there's enough modularity inside of Geth that we can actually do this. And so we use the same Ethereum emulator code that Ethereum uses. That's called the Geth core. We build on top of that something in the structure of our software, something we call ArbOS. This is the piece that does various bookkeeping and record keeping that you need to have a separate chain that's not exactly Ethereum. So this is what collects the fees. It keeps track of how much money the sequencer spent and makes sure that it collects enough fees to do that. It handles cross-chain communication and other sorts of things that are needed because we are not just a single standalone chain. And then on top of that, we have a bunch of node functionality. This does things like accept incoming connections from users and service their remote procedure call requests and various things like that. Now that component also in our software stack, a lot of that comes from Geth as well. So one of my colleagues calls this the Geth sandwich. You have Geth at the bottom, a little bit of Geth code at the top, and just this relatively small component in the middle that we created, which sort of changes the entire personality of what was an Ethereum node software and turns it into a node for our chain. Now, the state transition function, that piece I talked about before, that executes deterministically to take in one transaction, change the state, and produce a block, it's this orange piece. It's all of this Geth core plus some of this ArbOS piece. So the key takeaway here is that we figured out a way to structure this where most of the code that implements sort of the semantics of being like Ethereum is the very same code that Ethereum uses to do that. And that we've put that inside this orange box, which is a fully deterministic piece of code that does exactly the job we need to produce the next block in the chain. Yes?
Did you have to re-implement a lot of that or re-import from Ethereum when they did the big switch about a year ago?
Yes. So whenever Ethereum does what they call a hard fork, which is like a new major version change, there are updates to Geth which implement that, and we need to import those changes into here in order to be compatible. Now, when Ethereum did the big change from proof of work to proof of stake, that actually was in what's called the consensus layer. And this is what they call the execution layer. So actually, we didn't need to change much then. There were a couple of other updates that happened simultaneous with that we needed to import. But yeah, we need to track changes in Geth, and we need to be able to handle sort of hot version changes in the same way that Geth does. Fortunately, Geth already has that functionality built in. So we more or less just use Geth's mechanism for handling version upgrades. Yes?
Looking at that hardcore segment, were you building a community for the sequencer proof of work or proof of stake?
It's neither, actually. So yeah, so this is actually most blockchains, Ethereum, Bitcoin, and so on, they rely on consensus, right? Meaning you have a lot of different nodes, and it's effectively a voting system. And whichever outcome gets the most votes, in some sense, is the one that's chosen, right? We do not have a consensus algorithm. We have a correctness algorithm. That is, if Alice makes a correct claim and Bob and 1 million of his friends dispute it, Alice will win, because this dispute protocol actually will determine on the merits that one party is a liar. Now, technically, the computer scientist eyebrows are going up when I say that. The technical property is that the party who loses the challenge is guaranteed to have lied at some point during the challenge, and therefore we can mark that party as a liar and eject them from the system. So if there is any honest party involved in disputes, eventually all the liars will be ejected, and then the result that remains will be the honest one. Okay. All right. Now the last piece of it, this is, I think, one of the coolest technical tricks, is separating proving from execution. So one of the problems you have in getting high performance out of a system like this is that you need to have this very precise instruction by instruction model of execution for proving if there's a dispute to resolve the dispute. But what you want is to be able to have everyone compile the code to run on their own machine in normal operation. And the solution is basically to do both. That is, we take this software stack as I've shown it. You can take all of the blue things, you can compile them to native code, and you can compile it to native code and run that on your machine as an Arbitrum node. And if you trust yourself to have done that correctly, then you know that that Arbitrum node will execute correctly and give you the correct outcome. No one else ought to trust you, but if you built that yourself on your own machine, then you can trust that it's going to be correct. Okay. And so you could run that as a node, and in normal execution, normal users of the system are just taking this code and they're running it compiled to native machine code for whatever architecture they have, and that's, of course, the fastest way to run software. But if you need to prove, you want to compile this, if you want to have resolve a dispute or do proving, you want to have a portable way of agreeing on what the instructions are supposed to be. And so we take this orange piece, the state transition function, and we compile it using the same compiler, but to a different target, namely WASM or WebAssembly. WebAssembly is a portable, secure machine code format that was designed by a consortium of browser companies in order to be able to run untrusted code inside a browser. And WASM is really beautifully designed for our purpose. It's structured, it's type safe, and there are several excellent bulletproof implementations of it. It has clearly defined semantics. So we compile this to WASM, and you use that WASM in case there's a proof or a dispute. Now you might wonder, well, what if these compiled programs actually do different stuff? And the answer is, well, if you're going to be staking money on the result, then you should really be running both. And in fact, you can run WASM not too slowly, thanks to some really excellent just-in-time compilers. But for most users, they're going to run the native code as a node. That way you can run at full speed, at the speed of your machine. And if you need to fall back to proving, which happens very rarely, then you're going to use this slower but much more precise and portable WASM format. Okay. So there's a lot more that goes into the design of the system, and in response to some of the questions, I sort of hinted at some of the deeper aspects of this. But this is kind of a sketch of the tech that we've developed over the last few years. All right, let me change gears back again and go back to the story of sort of how we've gotten from where we started to where we are now. So here's a timeline with years along the bottom and various events through here. I'll go through these, and then our team size at various points in time. Right, so the initial academic paper was the summer of 2018. We started in early 2019 and got seed funding to start going. At that point, it was just the three of us sitting at Tiger Labs, like you saw earlier. In early 2020, we released our first testnet. A testnet is a version of one of these blockchain systems that is just like the real one technologically, except nothing real is at stake. We got Series A funding and Series B funding in the summer of 2021. Our first product at the end of August 2021. Notice, about 3 years from paper to our first product that our first customer gave us our first dollar for. This was a journey. We went through multiple iterations of the technology. We solved a lot of problems, especially around how to be compatible with Ethereum. Our first product, a year after the original product, we did our first major upgrade where we switched out the software stack almost completely for a separate one in this very sort of intricate and security orchestrated way. And in last fall, we acquired a company called Prismatic Labs, which makes the largest, which makes the most popular Ethereum consensus client. So we're able to sort of work across the layers of the software stack where we can do things where we get visibility into what's happening at the Ethereum layer on top of which we run. So up to 70 people right now. In terms of the amount of stuff going on, here is a graph of the amount of assets that have been deposited on our chain. Over time, you can see when we started. This is measured in ETH, the Ethereum native currency. They're worth about $1,500 each. So up at the right here, that was yesterday, I think. It's about $3.4 billion of assets currently on the chain. of which about $1 billion are dollars. So some metrics in terms of how much stuff is happening here. We've run about 135 million transactions, currently about 500,000 per day. About $3.4 billion of assets are on this thing. This, by the way, is terrifying. About $300 million of finance trading happen on the chain per day. Nowadays, 3.2 million unique user addresses, and about 200 new contracts, about 200 new programs deployed per day. There are, as far as we know, hundreds of companies have built products that run on this. So it's reached a scale that we really sort of didn't imagine when we started. Okay, so what are we going to do next? We're continuing to push forward. Some of it is just bringing more people into the experience we currently have. But we're also pushing the technology in a bunch of ways. The most exciting thing we have is a technology we call Stylus that lets you run untrusted code at near native speed on the chain and safely. That has a couple of advantages. One is it's probably another order of magnitude improvement in performance and therefore big reduction in cost. But also you get to write your program in whatever language you want. Those of you who know the Ethereum world, you have to use weird programming languages like Solidity. This will let you use whatever language you like, and so you can use legacy code much more easily. More decentralization. I talked about decentralizing the sequencer. That is the remaining component, which needs to be technically decentralized. We have a roadmap for doing that, and a protocol, and a draft protocol for doing it. The big trend these days is layer 3 chains, people building additional functionalities on top of this. Why would you want to do that? Aren't layer 2 chains awesome? Well, they are, but some people want things that are more custom. So people who want to customize, maybe they want to customize something about how fee collection works. Although I haven't talked about it, our chain, like every other chain, collects transaction fees from users, and we need to do that in order to cover our costs. As I said earlier, we are the largest user of Ethereum, and we spend we pay Ethereum many tens of thousands of dollars a day, and so we need to charge users fees. So maybe you want to customize your fee model. Maybe you want something else. So layer 3 chains or satellite chains are a thing that's definitely coming, and the general idea of giving people the ability to customize the functionalities that they're doing. Okay, so a lot of things going on. I've told you the story both technically and in terms of the journey. I'd be happy, I think we have some time, I'd be happy to answer any questions about the tech or the experience or really anything else. Yeah. Go up here.
Once the sequencer is decentralized, is there any use of continuing to use Ethereum as the underlying infrastructure?
Is there any value in using Ethereum? Well, if you want to interoperate with things and people that are on Ethereum, then yes. Ethereum is the base layer, right? And Ethereum serves often as a bridge between different layer 2 technologies. So a while back, there was this very influential sort of long essay written by Vitalik Buterin, who's the main architect of Ethereum, about what he called the roll-up centric roadmap. And this was the idea that Ethereum would more and more become a kind of security and settlement layer, and more of the activity would move to layer 2 chains like Arbitrum or our rivals. So I think that's where it's moving. Ethereum plays a really important role, but because it has limited capacity, it will really more and more take on the role of being the settlement and base security layer that everything else builds on.
The question was, you addressed at the very end about incentives and how
Yeah.
you and the community that run Arbitrum profit. I mean,
Yeah.
the biggest chain that doesn't do a coin of your own. And so I was wondering what was the thought process associated with not launching another coin?
Yeah. So one of the really interesting aspects of these technologies is that because they're open and have worldwide use, right, and they have limited resources, every chain has limited resources, you need to use markets to ration that resource. And so there's a whole fee mechanism. Ours is much like Ethereum. So, and it does a few things. One is it automatically, as needed, will raise the price if the demand for the services is above the chain's capacity, right? And it'll keep raising the price until the demand fits within the capacity. So that's one of the important things. That's purpose number one. Purpose number two is to cover the costs of operating the chain, right? The fees need to be enough to cover the costs, and they also need to be allocated in a reasonable way in order to align incentives. So basically that the fee that someone pays is proportionate to how much demand they actually place on the system's resources. And also so that the fee structure gives people incentive to use the chain's resources efficiently, right? So all of that is part of it. So there's then, within that structure, there is some money left over to cover our expenses. And essentially, transaction fees are the economic model. We've worked really hard to build the usage of our chain organically by providing a product that people really like and providing good support and so on, rather than rather than essentially paying people to use it. And we're really proud of the fact that we're the leader in our sector, despite being the only company in our sector that doesn't pay people to use our technology. And we think that's really just because we've delivered better, but you know, I'm kind of being a proud dad here. Andrew.
So you spent the last 25 years of your 28 years at Princeton being the expert on how really difficult it is even for companies that you think would know what they're doing.
Yep.
To build and deploy a secure system.
Yeah.
So how does it feel now?
So it's kind of terrifying, right? To stop and think that there are literally billions of dollars of other people's money riding on this technology. Now, you know, we have the advantage that all three of our founders have advanced Princeton graduate level or better training in computer security. But nonetheless, it's a really hard problem. And we do a bunch of things, right? So we do a lot of things in our development process, in testing, in simulation. We have a lot of real-time monitoring that is monitoring different invariants. There's some safeguards built in that are not so obvious. We hire the best security auditing firms in the world and get as much of their time as they'll give us. We think a lot about trying to build an architecture that is security friendly. And that's what it is. That said, you can't drive risk to zero.
So let me ask a complementary question.
Okay.
Which is, the security of Ethereum itself is continuing to be a research question.
Mm-hmm.
You know, the ability of somebody to borrow $2 billion to get enough stake to, cheat on
Yes.
the blockchain and that kind of thing.
Yeah.
So what do you do about that?
Actually, this one I feel more comfortable with. So the fact of the matter is that the security of Ethereum depends on a day-to-day basis on its protocol, and the protocol is complex. But also because Ethereum is a consensus chain, one of the advantages of a consensus chain is if there is broad consensus within the community that a thing that happened was wrong, that the community can, by strong social consensus, decide what the outcome was. It's very difficult to mobilize that, and it would require really overwhelming, social consensus in the community. But it is possible, and it is the ultimate backstop for the security of Ethereum. If something goes seriously wrong, the community can simply decide by overwhelming social consensus that a different result is the canonical one.
And has happened with the Dell hack.
It happened way back in the beginning of Ethereum. Yeah, in the very early days that happened once. But it has not happened since. But it is the ultimate backstop. And that's the best you can do in a worldwide system like this, is to rely on that kind of social consensus as a backstop.
But you don't have that mechanism, right?
So we do not have a social consensus backstop by virtue of being a correctness protocol rather than a consensus protocol. What we have, though, is the delayed certification time, and that actually gives time for action. We're going to be talking a lot more about this particular issue over the coming weeks and months, and so we'll have more to say about how we plan to address it. But
Have you ever had a dispute in this?
there's not been a dispute on our main net. Disputes happen all the time in our testing, and they've actually happened on test nets and on forked nets. So when Ethereum did its upgrade to proof of stake, the merge, that actually technically was a fork, where the main branch that everyone was on was the proof of stake branch, but the proof of work branch kept going. And when Ethereum forks, because we sit on top of it, we fork too. So there was a fork of our technology, which we called Arbitrum POW, proof of work. And there actually was, someone tried to cheat and submit a false history on the Arbitrum POW, and there was a dispute with one of our engineers on the other side. And our engineer won the dispute and took a stake of ETH on the ETH POW chain from the cheater. But of course, the ETH POW ETH were worth almost nothing, so he made like $8. Nonetheless, there was a dispute on ETH POW, and actually there was another fork chain where there was a dispute. So we know that it has worked in those cases. We do it all the time in testing. It's one of the things we test the most on every iteration of our software. But yeah, so the guarantee that we give is that if everyone is rational, disputes will never happen, the system will settle quickly. But regardless of what anyone does, that if two things are true, if Ethereum offers safety and liveness, and if there is at least one honest participant in our protocol, then we guarantee safety and liveness of our protocol. The other assumption is this, what I mentioned earlier in response to Pratik's question about censorship, that there is not censorship lasting more than 1 week in total during the resolution on Ethereum, during the resolution of any particular claim. But under those assumptions, we give the absolute guarantee.
A somewhat narrow question is that
Yeah.
you mentioned that the sequencer does have the power to like reorder things, and I was wondering if you or your group has already thought about is the future of that for the off-chain sequencers likely to be that you guys will eventually start doing MEV and people will just accept that, or you guys will commit to not doing MEV and people will say if they know what you're doing, or you'll try to cryptographically bind yourself to not if you have thoughts on how that's evolving. Many
thoughts. I'd be happy to talk about it more offline. This question is basically, as we move forward with our sequencer architecture to decentralize, there's this whole concept that lives in this space called MEV, minor extractable value, or maximal extractable value. Again, terrible terminology in this field. Basically, it's around the idea that someone who can manipulate the order of transactions or insert transactions can extract a lot of value from financial markets. And so the attitude we have taken is we do not want that to happen, right? We've used entirely first come, first served ordering and the secret mempool, meaning that you can't see what transactions have been submitted until they're already sequenced. There are some others who take the opposite approach, that they want to maximally monetize the opportunity to extract value by reordering. So they'll auction off to the highest bidder the ability to just make whatever transactions they want and put them in next. And so that is lucrative for the people who are operating the chain, but that money is being extracted from your users, and that's not how we roll. We depend a lot on the trust of our user community. And what we've told them is we will fight against attempts to extract value. That isn't to say value extraction can't happen. It's a complicated thing. But yeah, we've thought a lot about how to deal with this, how to minimize or eliminate the harmful kinds of reorder manipulation. And is it possible to monetize the forms that are harmless? As you know, there's deep waters there. We have always thought a lot about it. We'll be talking more about this going forward. JP.
Two things. One, I think maybe Pramod already asked a question about incentives and tokens, and is that the question you answered by earlier?
Yes, yeah. Yeah, we do not have a token. People use our tech because we offer a good value proposition.
You don't see reasons of incentives or something like that in your system to have that?
We don't need a token to generate incentives.
The second, the bigger question was, there's been a lot of advancement, as you also know, in ZK rollups and
Yeah.
things like that. And so what's your view of the future of how this is?
Yeah, so let me unpack that a little bit. ZK rollups, ZK stands for zero knowledge, which, as I said, terrible terminology in this field. So-called ZK proving systems used in this field, they're based on the fancy cryptographic zero knowledge proofs that people use in cryptography protocols, but they don't actually use the zero knowledge feature of those protocols, and so they're not technically zero knowledge protocols, even though everyone in the blockchain space calls them ZK protocols. Okay, so what are they? What they are is protocols that through super fancy cryptography allows you to produce a concise and efficiently checkable proof of what the result of doing a bazillion instructions of execution was, right? And so the question is, can we replace our assert and challenge type protocol with one where we just produce a concise cryptographic proof of what the correct result is, and everyone can check that proof and be done with it? And so the answer is yes, we can do that in principle, and we will do it when it becomes feasible at reasonable cost. But right now, the part of that iceberg that you don't see is the cost of generating the proof. And that's incredibly expensive.
You think that's very far away?
I think it's pretty far away to be able to do that at scale. You hear a lot of talk.
Yeah.
You hear a lot of systems. You even see some testnet systems deployed, and yeah, we'll start doing the proving later. Yeah. I don't think you're going to see that soon. Now, you do already see it for systems that just have certain limited and specialized transaction types. Like if all you want is say, simple like Uniswap style trades, if that's the only thing your chain needs to support, you can definitely do something like that in quote unquote ZK efficiently. But for general purpose computation, I don't think it's close to feasible. And here's the reason. The reason is pretty fundamental. So if a contract does an add operation, our technology, every node needs to do an add, right? If it's a ZK technology, you need to do the add and then do at least 1,000 elliptic curve operations in order to prove the result of the add, right? And so that's a huge performance hit and a huge latency hit because you can't, it takes a long time to do it. And you could do it in parallel, but as you know, parallelism doesn't reduce cost. It only reduces latency. So it's inherently a super expensive thing to do. So I think the type of architecture we use has a large and inherent long-term cost advantage. So now that said, if that turns out to be wrong, we could easily switch. Our architecture is entirely compatible with the other approach, but I'm not betting on that happening anytime soon. Matt?
You mentioned there's about 500,000 transactions per day. Do you have a sense of what those people are doing and how that's changed over time?
We know something about what kinds of applications they're using. They're mostly doing decentralized finance applications right now. We don't know everything because there are a huge number of contracts on the chain and uploading them is permissionless. Many of them have visible source code. What that means is they submit their source code to a third party who then compiles it and verifies that the result matches. So in a lot of cases, you can see the source code. If there's payments coming in, you can follow the money and figure out who it is. A lot of it is decentralized finance. Other significant areas, gaming and social applications. Social gaming is growing. One of the things that's true, though, is that gaming applications, at least interesting games, require being able to do a lot of transactions. And so the cost per transaction needs to be really low. And so for gaming to really become big in this space, we need to continue to drive down the cost per transaction, which currently is in the 10 cents-ish range on our chain, something like that. Yes, in the back.
Yeah, I was wondering what the motivation was with the Prismatic Labs acquisition.
Yeah.
It doesn't seem directly related, like the consensus layer. It seems like it gives you the functionality you need, so to go out there and buy it seems like a lot.
So it's a couple things. One is, in the tech space, whenever there's an acquisition of a small company, one of the considerations is the talent. And we were super impressed with the talent at that company. And having those folks on our team is actually really useful, number one. Number two, we believed, and I think that has proven out well as well, that having more knowledge into where the Ethereum protocol is and where it's going is actually pretty valuable in helping us do our jobs better. So to give you one example, I've talked a bunch about censorship attacks and so on, and the things that we need to do in our protocol to deal with the possibility of censorship. There's a lot of really active work going on in the Ethereum research community now about how to make Ethereum more censorship resistant and how to be able to detect censorship with an on-chain test. And some of the leading researchers on that problem is incredibly important to us. It requires deep knowledge of the Ethereum protocol, and some of the best researchers working that problem are on the Prismatic team that is now part of our team. So there's a lot of linkage actually between sort of at the deep technical level between the layers. And that's essentially what's going on.
Thank you very much for the talk. My question is, what is the bus factor of Offchain Labs?
What do you mean by that?
Bus factor. So if the sequencer was destroyed by a freak
Yeah.
accident of nature, what happens? How do you get the change?
Yeah, if the sequencer is destroyed, I didn't talk about it in the diagram, but there is a backup censorship proof mechanism where people can post their transactions directly to the Ethereum chain, and and then force their inclusion into the sequence. So that mechanism will keep operating. Who is the sequencer is something that is something that is configurable. There's the ability to change that. Currently, that ability is in our company, and we're talking to our community about how decisions like that can be spread across community members. So ultimately, you'll be able to use the backup mechanism, and then you'll be able to designate a new sequencer. But the longer-term path is to have a K of N committee of sequencers. And those, again, can be replaced, but at least if a few of them get run over by a bus, they'll keep going. So there is no component that is required for the Arbitrum chain to keep going. If our entire company and all of our infrastructure got, God forbid, destroyed tomorrow, the chain would keep going. This happened, for example, with the Ethereum proof of work chain. Right? When Ethereum forked, we followed the proof of stake branch. The Arbitrum chain on the proof of work branch, that kept going, even though we weren't doing anything, and people did a little bit of stuff over there. So I mean, the bus factor, I don't know if it's 0 or infinity, depending on how you count. But there is no, but our company is not required to exist or do anything for the chain to continue to operate. Me here.
Yeah, you started out by talking about the potential advantages for different kinds of operations to run compared to big tech and cloud computing. It seems like the biggest factor is cost, as you responded to Matt on that.
Yeah.
Is there another technology you can use for, instead of Ethereum, which is the biggest generator of cost,
Yeah.
that you can lower the cost of transactions for other kinds of services as well?
I mean, yeah, so we could, in principle, and our academic paper made a lot of this, that this technology can run on top of any layer 1 base chain. But we like Ethereum the best for a few reasons. First of all, it has by far the biggest, most active community of users and developers and so on. And so portability from Ethereum is important. And you can't really interoperate so closely with the chain if you have a different sort of underlying architecture. I think that's number one. Second, Ethereum from a security standpoint really meets our needs well. And then Ethereum is evolving over time. And it's moving in directions that will reduce that cost a lot. There's a bunch of changes in Ethereum in the pipeline. Probably, maybe, fingers crossed, this summer, Ethereum will adopt an upgrade called EIP 4844 that will provide much lower data costs for us. And then long term, there are other architectural things involving data sharding and redundant data storage that Ethereum is moving toward that should reduce those costs a lot. So I think of the high data costs as being a relatively temporary downside of using Ethereum. It is the biggest component of our cost right now, but I think eventually that will not be the case. Yeah.
So given that there has been, 18 months since Series B, what would you say would be your kind of 5 to 10 years vision for the company?
So a lot of it is around continuing to scale up what we're doing, right? So because our core value proposition is drive down cost, drive up capacity, we're not going to make response time any faster. We've hit the practical limit on that, I think. And then, it generates a kind of Moore's Law effect where new kinds of applications become possible, more people come in as the capacity goes up. My internal benchmark for how we think about, say, performance and capacity is we're aiming for a factor of 10 each year, which we have sustained so far, and we're on target to do that again this year. So just continuing to drive that is, I think, really important. Trying to make the developer experience easier is also important. We want people to be able to bring applications to this space and to build hybrid applications, which are partly sort of on-chain for some critical parts, but a lot of external stuff, also pretty important. And then continuing to drive decentralization. So that's sequencer decentralization and some other things that are in the pipeline. But fundamentally, we're mostly going to continue doing what we've been doing successfully so far. Continue to try to deliver that value proposition more effectively. Because honestly, I think one of the reasons we've been as successful as we have is we've been more focused on those sort of practical, measurable goals, rather than like trying to redesign human civilization from the ground up. Ari.
So does all code and data that basically all the applications, does that all have to be public? Or
Yes.
Okay.
Yeah, it's all public.
Have you thought about, situations where, some of these applications might want to compute on data that's only, that's private only to certain users?
Yes, we have. It's actually a pretty interesting problem, which you understand as well as anyone. And I should be asking you that question, but let me try to give an answer. Yeah, we thought about this a bunch. How can you have a sort of hybrid system where some users' data is private for them, and there's some things that we know how to do. We know how to have, for example, how to have a consortium chain where all members of the consortium know what's going on and nobody else does. That's not too difficult. That was in our original paper. But how to have, and there are ways to have accountability for an execution without everyone needing to know it. There's some really interesting and foundational computer science questions about how to combine secure multi-party computation with this public blockchain execution. Because although my trusted third-party story at the beginning, I still stand behind, but there is an asterisk that I didn't put on it, which is that your trusted third party can't keep secrets. Being able to do this where the trusted third party can keep secrets, which is probably possible with secure multi-party computation, some really interesting and foundational questions there. But yeah, so we thought about it some. We're not close to building anything like that at this point. Yes?
Last question.
Thanks.
You mentioned that a lot of the transactions are DeFi decentralized.
Mm-hmm.
What's the chance of a firm like Goldman Sachs being interested in buying you up?
What's the chance in Goldman Sachs?
Or Morgan Stanley?
Or someone? I mean, who knows what could happen? They're not beating down our door right now. Let me put it that way. I mean, the question of what,
They're a competitor in a sense, right?
in a sense, or we're a platform on which their competitors operate, if you will. I mean, the question of how big traditional finance companies move into the DeFi space or interact with the DeFi space, very interesting question. There's a lot of interesting business questions there. There's some interesting regulatory questions there. And we'll see how that develops. There are a lot of differences. And there is a kind of innovator's dilemma situation, sort of classic innovator's dilemma situation happening here, right? That's part of the story. I don't have a clear picture of where that will go, but like I said, right now they're not beating down our door.
We have time for one final question for us.
Yes?
Do you know if anybody co-locates with the sequencer? Like how far do they go?
Yeah. Yeah, people certainly do. Being able to get fast turnaround time from seeing a transaction that's published on the sequencer's feed to generating a transaction in response to getting one into the sequencer. Absolutely, we know people spend a lot of money and effort trying to minimize the time in that loop. That's a thing that definitely happens. And we've started to publish some, and we just started publishing some research we've been doing about ways of managing that so that it can become more of a market and less of people like spending money on co-location. I think there's some super interesting questions there, but yeah, that absolutely does happen. And we know that there's a bunch of parties who are doing that.